Wi-Fi Sheep would like to say a huge thank you to all of you that kindly support us. Help us continue to bring new videos like this. Join patreon.com/Wi-Fi Sheep from just $1 a month. Hello there and welcome back to Wi-Fi Sheep here on YouTube with me, Tom, and part 3 of our TinyBASIC Computers 8-bit build project. If you're not up to speed, we've started a brand new project here on Wi-Fi Sheep to see if it's possible to build a complete working real 8-bit microcomputer out of the bare minimum amount of parts and without the need for any major electronics experience or computer science knowledge. So far it's been a huge success, and I've set up a new playlist here on the channel, so if you're not up to speed you can check that out right now by clicking the box in the top corner of the screen and come back when you're up to speed if you want to. Now, last time we just finished building the main computer itself and we did the first boot and test, and that's where we left it. So in today's video we're going to cover how to actually program these computers, because it's okay once you've built them, but if you're just sitting there with a blank screen you're thinking, what do I do now? Now, as always with this series, it's designed for the beginner and the complete novice. We're going from sort of complete beginner's guide. So if you've never programmed before, then no need to worry. We're going to start at the very beginning and I'm going to talk you through in this video. If you haven't done already, do go and sign up for our free Facebook group. That's TinyBASIC Computers on Facebook. The address is facebook.com/groups/WFS TinyBASIC. And have a look on there already. Some of our group users have been posting their own build. Look at these fantastic machines that have been built. They're ready, they're working. To everyone who's done that, that is amazing and well done, and thank you so much for sharing. So if you do want to, go ahead over there and you can also download the required hex and ROM files, as well as some of the beginnings of source code that people have started to publish on the group. Again, the address is facebook.com/groups/WFS TinyBASIC. So before we go any further, I'll just show you my PCB board, what I've been working on. Now, mine looks a little bit different since you last saw it. I've been experimenting with a few add-ons, some modifications, things like that. I'm not going to go over what I've done in this video, but all you need to know is don't panic. Everything I'm going to show you today works exactly the same on the stock build that we built last week. So do not feel intimidated or worried about the modifications, but be assured I will go over them in good time in the new year with our next TinyBASIC Computers project. The reason I'm doing these upgrades is I'm getting the best possible setup ready for making a custom PCB to hopefully advance our project through to a full production PCB board. Speaking of PCB boards, and with Christmas just around the corner, there's still time to take advantage of the turnkey PCB assembly services provided by our partners at PCBGogo.com. These include PCB manufacturing and assembly, component sourcing, functional testing and IC programming. PCBGogo manufacturing bases are equipped with the most advanced production equipment, such as Yamaha pick and place machines, reflow oven, wave soldering machines, X-ray and AOI testing machines, all operated by highly trained technical personnel. PCBGogo is the leading specialist in surface mount through-hole and mixed technology PCB assembly and electronic manufacturing services, as well as turnkey electronic PCB assembly. PCBGogo provides an easy and cost-effective online ordering services from prototype to mass production. So join today. Sign up for your free account today at PCBGogo.com. Details and links are in the description. So our 8-bit system uses a form of BASIC called TinyBASIC. Now, BASIC stands for Beginner's All-Purpose Symbolic Instruction Code. It's not important, you don't need to remember that, it's just an interesting footnote. BASIC has been around since the late 1960s, and TinyBASIC was around since the mid-1970s and was one of the very first free open source programming languages ever made available in the computing world. And it went up against Microsoft BASIC, which at the time had just released for the Altair kit-based machines and cost quite a lot of money. In 2020, TinyBASIC finds the Arduino as one of its main homes. It's the Arduino single board computer microcontrollers that we use for the basis of our TinyBASIC computer build project. So without further ado, let's get on and let's have a look at how we actually program our TinyBASIC computers. So we've got our TinyBASIC computer breadboard system. As I explained, mine has changed a little bit from what we did in the last video, but that's not to worry about that for today. All you need to know is that we're still using a standard Arduino Nano, or in this case a clone board this side, and it's powered via USB from the mains. We're attached via USB to PS2 here into the connector and into the keyboard, and the video is going out via composite and then being upscaled to HDMI to go into a capture card, and that's what you're seeing on the screen now. So when we boot for the first time, we're greeted with this prompt. So TinyBASIC computer, the Wi-Fi sheep.co.uk, it says hello, and then it'll tell you what version of the ROM you're running. So in this case, it's 0.1 beta. And then it gives you a memory check. So in this case, there's 999 bytes of free RAM available, and we've got 1024 bytes of EEPROM space. That's just over 1K of EEPROM storage space available. We'll come back to that later. So the first thing we could actually do, if we wanted to, is we could actually just ask the machine to just tell us exactly what the memory situation is. So we type MEM and enter. And that will just reprint every time what the memory situation is with the computer. So as we add code, the top line, that's the 999 bytes of working RAM, will actually reduce, as you'll see. Okay, so what about programming? Well, the computer won't do anything unless we actually put some code into it. So let's just try, I don't know, let's type my name in. Let's just put Tom in, press return or enter, and it comes back as an error. That's not a surprise. Let's try putting a number in. So if I say 87, okay, so that didn't appear to do anything, but it didn't say error. Okay, so let's try putting something in a bit more structured now. Let's try a very simple loop program. So to do this, we'll type new for a new program. That'll clear the RAM. By the way, you can't clear the screen as you might do on other 8-bit systems. That's because the terminal, or what you're looking at in the video, the text that comes out on the screen, is a bit like a typewriter. So it's just printing to a piece of electronic paper that's scrolling upwards. You can't wipe it clean. That came with later systems, and something we might look at implementing here, but it doesn't do it in this version. So we can't wipe the text off the screen without doing a complete reset of the system, which we could do. We could hit the button to reset, and it'll just reload back in like so. Okay, so let's start with a program. So all basic programs start with line numbers. So we'll start at 10, and we'll ask it to print something to the screen. Print means to put a piece of text onto the screen. So we'll go print. Now we have to use quote marks. Now on this British keyboard, the quote is actually on the at, where it swaps the at and the to are swapped. So it's shift at for quote marks, not shift to. So we'll say print. Now whatever we put inside the quote marks will be printed. So let's just put Tom, shift, quote again. That's one line of code in. 20, go to 10, and that will tell it to go back to 10. So when we start the program, it's going to read line 10, print Tom. It's going to go to line 20, which will tell it to go back to 10, and it will just keep repeating the instruction, and that's called a loop. So we'll enter those in. If we want to check what we've actually got in the memory, we can type list, and that will reprint out for us the code. And now let's check the memory. And you can see we've used a few bytes there. So we're now at 974 bytes left of available memory for that 2-line program. If we want to test the program to run it, we can type run. And you can see it now more or less repeats Tom every line. You notice there's an at symbol appearing. That's just a tiny bit of distortion or interference on the serial signal. It's a little bug with this setup. It's nothing to worry about. It's just annoying. Now, one of the other major drawbacks is that we can't actually break out our program loop, unfortunately. Normally, on most basics, you could hit escape, or you could go Control C or Control X. None of that works here, unfortunately. It's not possible to break out of program loop once you set one running. The only way you can do it is to hit reset, which resets the computer. But now, if we try to list, we've lost the program, which is very, very annoying, and I appreciate how annoying that is. What I'm going to do is I'm just going to put our program back in. So there's our program back now in memory of the computer. So if we wanted to try and save that, we can actually save it to the onboard EEPROM storage on board the Arduino Nano. To do that, we simply type E, save. Now if I type E list, it'll list what it's got in memory. Again, you see there's a little bit of distortion between the 10 there with an @ symbol. Again, don't worry about that. And if we go run, we can now run the program as before. And if I want to stop it, I need to reset the computer. You now notice that the prompt has changed. It just says hello and the version number. That means there's actually something in the memory. And we can check that by typing mem. And you can actually see the bottom line there, there's 997 EEPROM bytes available. So there is actually something now stored in the memory. EList will show us the code. And if we type E chain, it'll run the program again. If we want to clear the memory, because bear in mind this is going to sit in the memory until we clear it. If we type E format, you'll notice some dots appear and it actually wipes the EEPROM storage completely clean. So if I now type EList, there's nothing there. And if I reset the computer again, you'll notice the command prompt changes on boot up. We get the full memory readout, meaning there's nothing in the EEPROM storage. So that's one way of saving your code into the internal memory. So you don't have to keep writing it in every time. Bearing in mind, you can only store one program at a time using this method. So I appreciate, again, its limitations with the system. Okay, so let's up things a little bit. Let's be a little more complicated. Let's use a variable and do some counting. So variables are a bit like a box. Imagine a box called something. In this case, we'll call it X. And that box can contain a number which can be called at a later date. So if I tell the computer, just off the fly, no line numbers, so just type X equals, let's put our number back in, 87. Okay. If I tell the computer now to print, and I don't need any quote marks because I actually want to call X the variable, not print X the letter on the screen, it comes back as 87. If I want to save a few bytes of RAM, I don't actually have to type print. I can just use question mark X, and that'll do exactly the same thing, and that will save us memory in the long run. So we can use variables which have to be single letters, unfortunately, so you've got A to Z to use, and you can store a number. What you can't do is you can't store text in a variable with this system. So if I even tried it, so D equals, let's try quoting, let's put TXT for text in there. It ain't having it. And even if you tried to do what other basics do, where you can actually use a $sign to denote a text variable. And bear in mind, this is perfectly valid basic on other things like Commodores, BBC Micros. This would work fine. Unfortunately here, if we try it, it just won't, it's not going to have any of it. It can only cope with variables being single letters and the variable itself being a number. So let's actually make that into a new program. So we'll just make sure we've got nothing in the memory. So we'll type new. So 10, we'll say that X equals itself plus 1. We'll now say 20 question mark X, that's short for print X, and then 30 will go to 10. Now before we run this, make sure we want to save it, so we'll go E save. Now let's run the code. And you can see this actually now starts to count by adding 1 to the value of X each time on the loop. And that'll just carry on counting until it creates such a big number, the machine physically runs out of RAM. So as before, we need to hit reset to make sure we escape our program. Remember, the program is still saved in the EEPROM, so we may need to wipe that now. So we'll go E format again. And we'll just wipe that clean. There we go. Brilliant. Okay. So one other thing I'll show you very quickly before we move on to looking at some basic breakout electronics is the sound. Now, if you have the sound version of the kernel running, and you can check that by memory, And if you come back at around, I should just type new and memory, there we go. So, and we come back at 999 bytes free as a standard stock boot up. That means you've got the sound module installed. The sound module takes about 50 bytes of additional RAM, but it does give you sound the computer can play. So on my model, I've actually got a little buzzer set up, but on the previous build, we actually connected it via composite leads to the sound of your TV or monitor out. So we can test this by typing tone, and then we need to give it a frequency range, so 400, and then a duration. So 1000 would be roughly a second. And there you go, and that will play a tone. And we can do the same again, so 600, which changes the frequency. Time. It does sound terrible through that buzzer, but you can see how it changed. And we can use these, we can add lines using the line numbering system, so 10, tone, equals, etc., if we wanted to. So before we go any further, the documentation for the complete TinyBASIC instruction set is available on our toolkit, which you can get from our Patreon. It's on our $3 tier on Patreon. Go to patreon.com/Wi-Fi Sheep, and they'll tell you all the instructions and commands that do actually work with this version of TinyBASIC. What I'm going to show you now is some Breakout Electronics, and this is really where I think these machines will be very, very useful. So we've got our main PCB board here, which I'm just going to push up there, and I've got this other little mini one, which is a half size. And what I've got is an LED attached here to a 1K resistor. So with an LED, the long leg is plus and the short leg is the negative or minus, and we're just bridging it over the gap in the middle of the breadboard. The 1K resistor is then connected and is bridging to ground or negative. Negative is jumping to negative, and then this is the black negative or ground wire that we're going to attach to our main PCB. This is the plus wire, which is acting as the white lead, and that's going to be attached to one of the data lines. Now, normally you'd want to actually turn this off before you plug things in. I'm going to do it with it still running. I do not advise this, but we should be okay. So I'm going to attach ground just onto the ground rail here. And on the top line, there's a row of pins. Some are occupied with the wires required for the PS2 keyboard input. However, a pin up here, the first one here labelled D12, is empty. And I'm going to plug this line, which can be my data rail, into the pin for D12. So that's the circuit set up. Nothing's going to happen. We now need to go back to BASIC. So in BASIC, I can now type D right, and I want to say pin 12, and I want to give it a value of 1. So I go comma 1. Now if I press return or enter, you'll notice that the LED has actually lit up. And I want to turn it back off. I can say D right 12, 0, and that will turn my LED off. So it should be possible to create a simple program to turn the LED on and off to make it flash using the loop method that I showed you. So let's start a new program, and we'll say 10 D right 12, 1, 20 D right 12, 0. Again, don't worry if you get a little bit of distortion while you're typing. 30, go to 10, which will create our loop. Let's just list our program again, make sure everything's okay. Yep, that's looking fine. And I'm going to do an e-save, just to make sure we actually do save it into memory, because we will have to reset the computer after we've tried. So let's see what happens. Now, in theory, this should flash on and off. Okay, well, the LED is very dim, but the LED is actually on. You'll just take my word for that. So there you are, because it is actually on. But what's happening is that we're running so fast. This computer's clocked to 16 megahertz, which is very, very fast for an 8-bit system. Most 8-bit computers of today, things like the Commodores, the ZX Spectrums, were clocked to anything between 1 to about 6 to 7 megahertz, if that. So basically, it's running so fast that it just makes the bulb appear dull because it's actually flicking on and off so fast we can't see it with the eye. So what we need to do is we need to create a delay line so we can actually see the physical flashing on, off, on, off. So let's reset. And let's E-list our program. So what we could do now is add some delay lines. This is why we go up in tens, because it means I can squeeze additional code in between 10 and 20. So I could say line, let's see now, line 15, delay, open brackets, and let's say 400. And then we'll need to do line 25, delay 400. Let's list again. And you can see it's now added those new lines in order of our program. So now we'll just type E, save once more. Now let's run again. And now you can definitely see here that the LED is flashing on and off because we've created a pause between it turning on and it turning off before it loops again. Now let's just see how much memory that actually uses. So yeah, about 80 bytes of memory for that short program, which we'll list again so you can see it. So even with 999 bytes, it's just under 1K of RAM. It's still possible to write useful little programs, and I have been dabbling around with even longer bits of code. So as you've seen, it works and it's very programmable despite the quite severe limitations that our system actually has. However, despite the fact you can use the eSave function to save a program into RAM to come back at a later date, it can be a little bit tedious, especially if you want to swap programs regularly or on the fly. There is, however, a solution for this, and it involves going back to our PC that we used to flash our Arduino boards with originally. If you've got access to the full toolkit, there's a program in there called Putty, which is a freeware serial port connector. And this actually allows a Windows PC to connect directly to the Arduino board powering the main system. It means theoretically that we can actually write BASIC in TextEdit or Notepad or whatever you want to use, or even copy and paste straight out of our Facebook group and actually paste straight into the Putty terminal, which will then transfer the code straight through USB to our main Arduino board driving TinyBASIC. This way we can actually save and upload longer programs, and we can actually edit things in a PC environment that's a little bit more modern, and we have things like a delete key for the very first time. If you're not aware of our toolkit, it's available to our patrons. That's at patreon.com/Wi-Fi Sheep. And it basically contains all the latest updated versions of the hex ROMs for the project, as well as a collection of free open source software that we've brought together that we use as part of our TinyBASIC Computers project. Again, if you want to join, it's on our $3 tier, and that's on patreon.com/Wi-Fi Sheep. So let's take a look at how this actually works. So I've got my PC laptop here. This is an older Windows 7 Hewlett-Packard Pavilion, I think it is, laptop. We used this in the last video when we actually flashed the hex ROMs to the Arduinos. So this already has the correct drivers installed, and I've got my TinyBASIC toolkit on screen here. And if you haven't done already, you will need to install the Windows software drivers. That's the CH340 drivers for Windows, if you intend to use the clone Arduino boards that we're using here. So one of the programs in the latest version is Putty, which you can download for free. This is a terminal application for Windows, and we can use it to connect directly to TinyBASIC on the Arduino board via a USB/serial connection. So the Arduino TinyBASIC computer is now being powered from the micro USB through to a USB, standard USB on this laptop. So with that connected, we now want to click serial, select which port that is on, which I think is port, well, it might be on 6, let's check. And also we need to make sure that the baud rating is set, as the speed in this case is set to 300. If I click open, and there we go, it's actually opened, and you can see that it's actually loaded the hello and the version number in a new Putty window. Meaning if I now type on the laptop, so let's ask for the memory again, you can see that it actually now comes through on the main interpreter terminal on the TV as well. And this means we can now remotely control our TinyBASIC computer from a PC laptop, which is great, but this also has one huge advantage. If I go back into my toolkit, there's a folder here called Program Listings that has a Guess No V1 program as a text file. So if we open the program up, it's just a text file. We can see we've actually got a basic listing, and because we're in a modern text editor, we can actually move around, copy, paste and change things as we want. What we can do is we can copy the whole piece of code, copy to the clipboard, and if we go back to our Putty terminal, if we just right click in the space anywhere, you can see it'll start putting the code into the TinyBASIC interpreter. So let's just list that, see what we got. And there is the program is now actually in the memory of the machine, and we haven't had to type that all in by hand. So let's do another e-save. Again, I'm just typing here on the laptop, or I could come over and type if I wanted on the keyboard of the machine itself, and you see it comes back onto the terminal, no problem. So let's e-save. And now let's have a go at running that program, see what we get. So this is a simple numbers game, so it's asking me guess the number. It should be I am thinking. Guess the number I am thinking of between 0 and 10. So we now have to sort of put a number in. So 6, nope. 8, nope. 0, 6, no. 7. Oh, 7. There we are. We won. Badly. And then the program stops, which means we could just time we can have another game. So you could see the advantage of using Putty and Notepad together. You could actually write listings or download programs or even copy and paste out of our Facebook group straight into your computer, into your TinyBASIC system, and then you could do an e-save to save. It also means you don't have to connect to monitor, which is great, and I think this is going to be a really, really useful feature to help develop code for the TinyBASIC system. Well, that brings us to the end of this demonstration right here on Wi-Fi Sheep. If you've been following along, then I hope you've had the best of success with our TinyBASIC Computers project. We'll be back in the new year with more content about TinyBASIC Computers, including explaining my add-ons for the project and also some slightly more complex projects going forward. In the meantime, if you haven't done already, please do join us on Facebook. Our TinyBASIC Computers Facebook group can be found at facebook.com/groups/WFS TinyBASIC. It'd be great to see you there. If you're brand new to the channel, thank you so much for your company. Do not forget to like and subscribe, and I will see you real soon right here. Until next time, bye for now.